Okay, so in this video, I'm going to be going over the derivation of the logistical regressions cost function and its gradient. We're going to take it from like a mathematical form to a matrix form so that we can plug it into MATLAB. Okay, so this comes from week 3 of the Coursera's machine learning course by Stanford University, taught by Andrew Ng. At the end of the weeks, starting at week 2, we have these programming assignments that are done in MATLAB. So for this week's assignment, we have these files here. And there's a main file that's a notebook. I guess it's called a live script. And what we do is fill in the blanks for the functions that these live scripts call. Like here, plot data was a function that we had to fill in. I wrote this here. Okay, like sigmoid is a function that we wrote, blah, blah. And this video, I'm going to be going over the cost function, how to derive that. At the end of everything, we only have 2 lines of code. But the derivation is multiple lines. I LaTeX it here on my overleaf. Okay, so a few things to note. Superscripts are rows, subscripts are columns. The matrix X, the way it's structured is that each row corresponds to a sample. And let's see, Y and theta are column vectors of target values and weights respectively. I use a shorthand notation for the hypothesis of a particular sample. So the hypothesis of the ith row of X, I'll denote that as HI. The log of H is a vector of the log of each of those values. Okay, cost function. This one's fairly straightforward. Start with the cost function and note that we are summing the product of each of the vector's entries. Here's one vector, here's another vector. One vector, here's another vector. And that's just a dot product. So we have y dot this vector dot this. To turn it into matrix form, we just take the transpose and multiply it out. The gradient of the cost function. Shorthand, I use partial sub k to denote the partial derivative with respect to theta k. We note that the derivative of the sigmoid function is this, sigmoid times 1 minus sigmoid, so that we have this right here that we're going to use in like step 2. So the partial k of hi, right? Remember, hi is a sigmoid of something. It's a sigmoid of this. That becomes sigmoid of this times 1 minus sigmoid of this. And going back up here, note that whatever this is, the z is the dot product of theta and the ith row of x. So partial with respect to k of that is just the ith samples k column. So the ith samples kth feature. We could simplify this by replacing the sigmoid of whatever with hi. Because remember, hi and sigmoid of this. See that? All right, taking the partial of the cost function. Look at this cost function here. inside the brackets are scalars, right? They're the entries of these vectors. So we just do regular calculus. We do a chain rule, product rule, and get this inside here. We replace partial KHI with this, see? And its corresponding form for 1 minus H here. Cross out HI on this side, cross out 1 minus HI on this side, and we are left with this. With some distributive property of algebra, we can simplify to yi minus hi times xik. Oh shit. There's a summation there. Okay, we have that, and in turning the matrix form, we take the transpose of x and multiply it by this vector y minus h. And this is how we get this. Okay. And the resulting answers that we get from filling in this function is correct. They give us values here to verify.